Welcome, everyone.
Welcome.
I'm Romain Guy from the Android framework team, and now can finally reveal some of the stuff I've been working on.
And I'm Lucy Abramyan. I'm an engineer on the AR and VR team. I'm actually going to start off by telling you something very personal to me and that I'm very passionate about. But it's not just one thing. It's actually a combination of things that I love. Ever since I was a child, I've been marveled by space. Isn't it amazing? Just think about it for a second. The diversity of the planets, everything that's going on around the solar system right now. Wouldn't it be amazing if we could just see it up close? There's just one problem, though. Humans can't go to another planet, not even Mars, just yet. Or can we? And this starts the second part of my passion. Augmented reality is delightful. It helps you interact with a world that is within a whole new experience that is catered to your environment. ARCore is Google's platform for augmented reality applications. But even if we use ARCore to help us understand the environment, what do we do about 3D rendering? OK, so while it's not exactly rocket science, today 3D rendering has a steep learning curve. But if you're like me, you're still really passionate about space and AR and 3D and rendering and graphics and matrix math, so you just start coding. And coding and coding and coding, and then you quickly realize there's a lot of code.
Yeah, actually, how many of you have written OpenGL in their developer life? So first of all, I'm so sorry. And second of all, you probably know how difficult it is. I've been doing this kind of stuff for basically 10 years at Google, and it's a pain.
This proves my point right here. It's difficult. And we've noticed that there's so much in common throughout all AR apps, things like streaming the camera image to the background, or even just making an object appear on the screen. So we wanted to take care of that, so you don't have to go through all the pain.
No, I go through the pain.
That's why we built the Sceneform SDK, to make AR development quick, simple, and familiar to any Android developer. Sceneform is a 3D framework that makes it easy for you to build ARCore apps. It includes an Android Studio plugin that allows you to import, view, and even edit 3D models. The API offers a high-level way of working with 3D, and it's tightly integrated with ARCore, so that makes it especially easy to build AR apps. Because it integrates with the Android View framework, you can easily add AR into an existing app or create one from scratch. The New York Times used Sceneform in their new AR articles. You can download the New York Times app today and search for augmented reality, and not only read about David Bowie, but also walk around a mannequin wearing his costumes. Otto, the online furnishing retailer, used Sceneform to allow customers to see what a piece of furniture looks like in their living room before they buy it. If you're from a European country, you'll be able to download the app and try it out.
And actually, a couple of the engineers from Otto are in the audience somewhere. And I just want to thank them, because they were very patient with us when we were working on Sceneform. They went through all the early versions of the API. And it wasn't always working right. So thank you.
Thanks for your patience. Well, thanks for helping us build it.
Yes.
Yes. I'm going to play this video again, because I love it. Remember that solar system I was talking about that I wanted to bring to you? Here it is, right inside your living room. And trust me, without the thousands of lines of rendering code. You can see this code online right now by going to our GitHub repo linked at the end of the presentation. So let's walk through how we built this app. So first, we'll start off with some common concepts of AR apps, and then show you code snippets using Sceneform. After we've covered the basics, Romain will go into detail about physically based materials and give you all sorts of rendering knowledge to help you optimize and make beautiful 3D objects in your app. The Sceneform API consists of two concepts, the scene and the view. The scene represents the objects you are adding to the world, like the 3D models that you want to place in your AR app. The view is where your scene will be drawn. In this case, it's your device screen and where the device is in the world. The renderer will draw the scene from this perspective. The view ties into the Android View framework or system, and that's your hook into the app. As a developer, you will build your scene by defining the spatial relationships of objects. To do this, Sceneform provides a high-level scene graph API for defining the hierarchy of objects and their spatial relationships. One analogy that I like to think about is the Android View hierarchy, but instead of, obviously in 3D, and instead of views, we use graph nodes. Each node contains all the information that Sceneform needs to render it and to interact with it. And finally, nodes can be added to other nodes, forming a parent-child relationship. In our solar system example, planets orbit around the sun, and moons of these planets orbit around the planets. A natural way to define the solar system in a scene graph is to make the sun the root node, and add planets as the sun's children, and add the moons as their children. That way, if you want to animate the Earth orbiting the sun, the moon will just follow the Earth. You don't have to do the complicated math to figure out the moon's relationship to the sun while the Earth is orbiting it. In this video, it's the same solar system example that we saw a little bit ago, but we've also added touch interaction. Nodes can become interactive by adding touch listeners to them, obviously. And we propagate touch events through the scene graph the same way Android touch events are propagated through the view hierarchy. Nodes can contain 3D models, like the planets or the sun, or 2D Android views. You can create an Android view just as you would in your layout editor and put it in the world and interact with it like you would with any other app. It's a first-class citizen of our scene. So how does an Android developer usually get started? With Android Studio, of course. I won't go too deep into this because there is another talk tomorrow morning called Build, Iterate, and Launch that will show you all of these steps. But I want to note that we have built a plugin for Android Studio that allows you to drop in 3D models that are built with standard modeling tools like Maya, or you can download them from Poly. You go through the import flow, and that converts the models into an SFA and SFB format. These formats are particular to Sceneform, and the SFA is what's bundled into your app. So drop the SFA file into the res-raw folder, or the source assets folder, and you can ship it with your app. One thing we wanted to note, yes, you can view and edit your models right there in Android Studio.
Yes. And what's important to note is that we use the same renderer on the device and inside Android Studio, so what you see in Studio will be what you see on the device. One other thing to note, again, there are going to be more details tomorrow. The importer acts as a Gradle plugin, so for every asset that you import inside your project, you're going to get a new Gradle task, which means that if your designers give you a new version of the asset, all you have to do is replace the file in your project, and the next time you build, we will reconvert the asset automatically, and you'll be up to date. So you don't have to worry about going through a manual wizard every time you get a new version of the asset.
Let's start coding? Yeah. Let's start off with our onCreate method in your activity, just as you would. Find the AR fragment, find Sceneform's AR fragment This takes care of setting up the ARCore session for you and also manages the lifecycle of Sceneform. And naturally, it will contain the AR view, and the view holds a reference to the scene. I want to note here that you don't have to use our fragment. You can use the view and therefore the scene directly.
And this is one of the powerful things about Sceneform, because it's just using a regular Android view that happens to be a surface view. You can drop it wherever you want in your application. It doesn't have to be full screen. And more importantly, we don't take over your application. If you try to use something like Unity, for instance, Unity becomes your application. It's a very easy way to embed AR inside an Android application that already exists. And New York Times, for instance, is a great example of how far you can push this, because they show AR through a web view. So they just put an AR view behind a transparent web view. And as you scroll the web view, they load content into the AR view. So you can do pretty complex things. It doesn't have to be just a simple full screen example like you're seeing here.
So let's start loading all of our models. And in this case, I have a to-do for you to load the rest of them. But I'll show you how to build a 3D model. In Sceneform, we have two types of models. We call, or not models, sorry, renderables. Renderables are the things that are going to be rendered on the screen. I know we're very creative with the naming. In this case, we want to load the sun model, which was dropped into our res.raw folder. And so you set the source and build. I also want to point out that these are completable futures. So it will do the loading in the background, and you can accept and handle as you would with a completable future. I should also mention Kotlin here. We could do all of this in Kotlin, but all of the code snippets will be in Java.
One thing we haven't done yet is build Kotlin extensions for Sceneform, but if you are inclined to do so, I would love to see your code.
So remember earlier we showed you this graph representing the sun and the planets. Keep the structure in mind, because we're going to be loading and creating the scene graph. We've loaded all the models, so now let's build a solar system. We start off with the sun node. Create a new node and set its renderable to be the sun model that you had loaded. Next, we create the earth node. We set its parent to the sun, therefore building the scene graph, starting to build the scene graph. Notice here that I have set the sun to earth meters constant. In this case, I've used 0.5 meters because I wanted to fit the solar system inside the living room. But we've set the Earth's local position relative to its parent, the sun. Set the renderable that we loaded, and continue. Now the moon. Create the node, set the parent to Earth, and notice here now that the local position of the moon is Earth to moon in meters. I think I've set it to be 0.1. It has nothing to do with the sun. Set the renderable as a moon renderable, and you're set. Now, to animate their orbit, you can just use Android's property animation system. We've created some evaluators for you to use. Once we return the root node, we now have the entire graph, our solar system. So let's bring the solar system into the scene. All we have to do is parent it to the scene. And that's it, or parent the sun to the scene. And the solar system is now in your room. Or we could do something else. Anchors, I don't know if you know about ARCore anchors, but they are how you attach your content to the world. And ARCore makes sure that they are anchored to the world. You can get anchors from ARCore's hit test based on the user's touch events. Or with our new cloud anchors, you can use an anchor that another friend has created on another device. For using anchors, we've created an extension to Node called the anchor node that just takes an anchor and now brings that anchor into our scene graph. Set the anchor node's parent easily, just to the scene, and then set the sun's parent to the anchor node. Notice how we've rearranged it a little bit. First, we had the scene with the sun as a root node, but now we've created the scene, the anchor node, and then the sun and the rest of the solar system. I was mentioning model renderables before, so now we'll talk about the 2D view renderables. To add 2D into your app, in this case, I've used a little info card that pops up about a quarter of a meter above a planet, say, and you want it to display some information on it. So I've created this node that would hold the view renderable. I've set it to a planet, and it will now float a quarter of a meter above the planet, wherever that planet is. You start off by building a view renderable. But notice here that instead of the res raw source for the model renderable, I've set it to the view ID. And that's all there is to it. Now you have the 2D view, just as you would have in any other application, and you could do things with that view, like set the text. And finally, if you want to drag, scale, and rotate objects, we made that really easy for you by creating a transformable node. The transformable node is an extension to Node, but it also understands touch events and gestures, like dragging and scaling and rotating objects. So in this case, if instead of creating a sun node, I created a transformable sun node, I would just do everything else that I did before, but now we can actually drag and move the solar system. I should mention that there was a talk earlier today about UX interactions in AR. So if you want to know more about the best practices for UX, please go back and look at that talk. I'll hand it over to Romain.
Let's talk about materials. So this is a deceivingly simple part of Sceneform. But before you can understand how to create your own material, we have to understand the concept behind physically based rendering. So after you import an asset through the Android Studio plugin, like Lucy said, you end up with two files. There's a .sfa and a .sfb. So the .sfb is the binary that goes into your application and that will load at runtime. The .sfa is effectively a JSON description of the asset. And it looks a little bit something like this. So this is the SFA from the moon, the moon of the Earth from our example. And you can see those attributes called base color, normal, and metallic roughness. So those point to textures that are defined somewhere else in the SFA file. I'm not going to go into details about the syntax and the structure of the SFA file, mostly because there's excellent documentation that's available online. There's also the talk tomorrow morning, so you should check that out. But what I want to talk about is what kind of textures do you need to create to be meaningful for the color, the normal, and those two weird ones, the metallic and the roughness textures? But again, before we do this, we have to talk about physically based rendering. So physically based rendering has started becoming quite popular over the past, I would say, 3 or 4 years. It started in the VFX industry. It's now used in a lot of AAA games. It's still fairly uncommon on mobile. And the basic idea behind it is that we're relying on physical principles to define all the behaviors and all the equations that we use in the rendering system. So that includes things like separating the lighting code from the code that defines the surface, and that doesn't impact on the materials themselves. It means that we have to take into account laws of physics like the energy conservation. We use physical light units. So for instance, when we declare a sun as a dynamic light in a scene, we use the unit called lux. Or if you were to add a light in your scene, in your AR scene, that's just a light bulb, you can use watts or lumens as the unit. So it's a number of things like this that are grounded in reality that both help us validate our rendering. It also makes our life easier because those are things we deal with every day and that feel natural to us. I'm going to show you an example. So this is an example, it's not in AR, but this has been rendered using our rendering engine, just a very simple sphere. And you can see that there are reflections on the sphere. You can see, what you are seeing here in action is a physical effect called the Fresnel effect after a 19th century physicist. And the closer you are to the edge of the sphere, the more you can see the reflections. And this is a natural phenomenon that you can see everywhere. So this is a photo I took in Lake Tahoe. And you can see that close to the edge where I was standing, you can see through the water. And the further away you get, the more you can see the reflections of the water. So, and again, you can see this on every object. Every object around you follows this principle. It might not be obvious at first, but this is what happens. And we'll recreate this kind of physical behaviors in our rendering engine to make things look as realistic as possible. So we follow a workflow for our materials called the metallic roughness workflow. If you look that up, you're going to see there's a lot of information out there. The metallic roughness workflow is available in a lot of popular tools. If you've used Unity 5, you have access to it. Unreal Engine 4 uses it. Blender, recent versions, has access to the metallic workflow as well. So the way it works is when you want to define a new material, you are actually trying to describe and define a surface. And to define a surface, you're going to need three things. And we're going to take them in this order for very specific reasons we're going to explain in a little bit. The first one is you need to define the metallic property of the surface. Often we talk about metallicness, but it's not even a word. So metallic, at a high level, is whether or not the object is a metal. And we're going to see why this is very important to us. Then you're going to define the color of the object. And we call it the base color as opposed to the diffuse color or the specular color. Those are terms that you might have seen if you've used older engines. And again, there's a reason for that. Finally, you need to define something called a roughness. Roughly, it means how shiny the object is. And if you want to go further, there are two other things you can define to give your surface more details, a more natural appearance. So the first one is the normal, or the normal map. It just helps break the evenness of the surface. And the second one is called the ambient occlusion or occlusion. So first, what is a non-metal? I'll spare you the equation. This is actually fairly simple. So here at the bottom, we have an object, an orange object. It's drawn in gray to make the diagram easier to read. But we have light coming from a light source and hitting the surface of the object. And the light that hits the object gets split into two components. The first one in white is the reflected part. So those are all the reflections. So in that orange ball that we saw before, at the edges you could see those reflections. That's this part of the light. And then the other part of the light is refracted into the object. And most objects around us, they absorb some of the light. The light enters the object, it gets scattered, it bounces around inside the object, and eventually some of the light will come out, but not all of it. And this is what gives object colors. In that particular case, because the object appears orange, it just means that green and blue components of the light have been absorbed inside the object. And that orange light that comes out is called the diffuse light. The white light is called the specular light. So specular is for the reflections, and diffuse is for everything else. So this is an example of a non-metallic orange ball, and you can see those reflections. If you look at the reflections here, this is simulating an environment inside the classroom where we have overhead white lights. And you can see that even though the object itself is orange, the lights appear white. That's because they just bounce off, they don't enter the object, they don't take the color of the object into account. And then the rest of the object, the non-reflective parts, are orange as expected. Now, when you have a metallic object, metals are conductors, and they're called conductors because when energy hits them, in this case light, the part of the energy that's refracted into the surface gets absorbed. It just gets transmitted into the object and does not get scattered outside. So there's no diffuse light. You only get reflections. However, what happens with those reflections is that they take the color of the object. So you don't get those white reflections anymore. You get the orange reflections instead. So if we take the same ball that we just saw and we turn it into a metal, if you look again at the lights, at the overhead lights of that classroom, you can see that they now appear orange. And this is because the rest of the light, the rest of the specular light, was absorbed inside the object. You can also see another side effect of this, of the Fresnel law that we just talked about. If you look at the edges of the sphere, you can see that the reflections are not orange anymore. They take on the color of the environment. And this is, again, a very natural effect. It feels weird when you see it for the first time in a rendering engine, but rendering engineers like me, who are obsessed about their work, comes Christmas time, they look at their Christmas tree and they take a picture of one of the ornaments. I was holding one of my phones on the side. I was lighting this green metallic ball with an orange light from the wallpaper on my phone. And you can see that on the edge of the ball, suddenly the reflections are not green anymore. They take on the orange light coming from the light source. So what we just saw here can appear weird when you see it on the computer for the first time, but this is an effect that's perfectly natural that happens everywhere around you. So the metallic property, I mentioned that this is the first thing you should decide, and you've now seen why, because when you define the color of your object, when you define the base color, it's whether or not, depending on whether or not your object is metallic or not, it's going to dramatically change the aspect of the surface. So you should always decide first whether you're dealing with a metal or a non-metal. So when it comes time to create the actual texture, the metallicness of the object can be defined as a grayscale texture, so values between 0 and 255. At 0, the object is not a metal, and at 255, when it's white, the object is a metal. Most of the time, the value should be either 0 or either 1. All the values in between are mostly used for anti-aliasing purposes, because your texture could contain, maybe it's a metal that's painted, and the paint itself is not a metal. So at the edges of the paint, you want nice fall-offs, nice transitions from metal to non-metal. Certain alloys in real life happens to be a mixture, and you can use intermediate values as well, but most of the time you won't have to deal with it. You won't have to worry about it. Very quickly, when a metal gets rusty, it actually becomes non-metallic. So if you're trying to create a surface that's rusty, the rust stains will be non-metal. And very often, so that's something that, again, you'll see tomorrow, you don't have to use textures for everything. You can also use constants. And very often, you can get away with not having a texture for the metallicness of your object. You can just say either it's a metal or it's not. OK, next step, you have to define the base color, so the color of your object. It defines either the diffuse color of the object for non-metals, or the specular color, or the color of the reflections for metallic objects. And what's quite difficult to do when you create a base color texture is that it must be completely devoid of any lighting information or any shadowing. And we're going to look at an example. And that can be hard because as human beings, we never see the actual color of an object. We only see objects through lighting. So it's difficult to imagine what it looks like, but you can quickly get used to it. And whenever you use a tool like Photoshop or Affinity Photo to build your textures, make sure that you're working in the sRGB color space, which is what this tool should be doing by default. But just in case, make sure you and your artist work in that color space. So this is a quick guide of how to build colors for objects. Based on real-world data, most of non-metallic objects use most of the range of the brightness. So whenever you pick a color in the color picker, for a non-metallic object, the values of your RGB color should be between 10 and 240. And there's nothing as dark as 0. There's nothing as bright as 255 when we deal with non-metals. And metals, on the other hand, they're always fairly bright. So they are not, dark metals basically don't exist. So you should stay in the range that's shown up here. And I was mentioning that you should not have any lighting information inside the base color of your object. And you can see here a set of swatches taken from real-world observation. And you can see that gold, for instance, that in real life appears quite yellow and saturated, the base color is actually not that saturated. All the colors in the base color map tend to be very pale compared to what you actually perceive. So here's another example. On the right, you can see a material to represent bricks. And on the left, you can see the base color texture. And you can see the difference. Once we light the object, all the contrast and saturation appears. But all of that information is not in the original texture that we're using to create this material. So again, if you work with your artist, make sure they're familiar with the metallic roughness workflow, or make sure they at least understand that the base color map should not contain any lighting or shadowing. Now, I mentioned the third parameter is called the roughness and defines how shiny an object is. So a very simple way to define a surface is like this. It's infinitely smooth. There's no object in the world that's smooth. And what happens when you have a smooth object, rays of light that are coming parallel to each other bounce off parallel to each other as well. So you get very sharp reflections. Rough objects, on the other hand, have what we call macrofacets at the surface. You can think of those as very, very tiny mirrors that might not be oriented in the same directions. So when light comes in, you have these parallel rays of light. They can bounce off in random directions, and that creates blurry reflections. And those are examples. At the top, you can see a ball, a yellow metal, and we increase the roughness from 0 all the way to 1. And at the bottom, we have a non-metallic ball, and we increase the roughness from 0 to 1. And you can see the effect here. We start with very sharp reflection, and as we get closer and closer to 1, the reflections become so blurry that we can't even perceive that they are reflections. They're there, but they're spread over basically the entire surface, the entire visible surface. So this is a very powerful feature because it lets you, again, create things like polished metals or a plastic that has been used for quite a while and it's become, well, basically rough. So roughness is very similar to the metallic property. It's a grayscale texture. You use values between 0 and 255. At 0, your surface is going to be glossy or very shiny. At 255, it's going to be extremely rough. You're not going to be able to see the reflections anymore. And just be aware that there might be differences between different tools. So if you specify roughness of 100, let's say in Blender, that same roughness might look a little bit different in a different engine because there are different ways of doing those computations. You shouldn't worry too much about this. Just tweak the asset until it looks right instead of Sceneform. Sometimes the roughness will be called glossiness instead. And glossiness is just the opposite value, so you can just invert the texture in Photoshop, for instance, to get the roughness map. Next, we want to add some details. So to save on performance and memory, we try to use smooth surfaces. So when you build your mesh made of triangles, you use smooth surfaces. So here we have an example of bricks that are completely smooth. To add some details, we can use a normal map. A normal map looks like this. When you apply it to the object, suddenly you get a little bit of shadowing and more information, more details on the surface. I'm not going to go into too much details about normal maps because there's a ton of information available online, so we're going to skip that before we run out of time. The only thing to know is that the colors inside of a normal map encode a vector. It's a direction. It's not a color. Next one is ambient occlusion. So here we have our bricks, and they've been textured properly. They have a roughness, they have a metallic, they have a normal map. But we're lacking what we call macro-scale shadowing information. Because a brick has a depth, so it will create shadows on itself. Like the surface should be casting shadows on itself. But because we don't have access to the triangles, instead what we create is just a black and white texture that tells us where the shadows should be. So again, that's called ambient occlusion or occlusion. It's very simple to, let's see the before and after. That's after, before, after. So again, adds a lot of detail and depth to your object. An ambient occlusion map is just a grayscale texture. When the values are 0, the pixel is completely in the dark. You should never have values set exactly to 0. At 255, there's going to be no shadowing. And it doesn't affect all the lighting. I'm not going to go into too much details here. So anytime you create an object that has cracks or crevices, that kind of stuff, you should be using an ambient occlusion map. So in the end, we have our 5 textures. We have the metallicness, the base color, the roughness, the normal, and the ambient occlusion. And if we get them all together in this particular example, you can create an object where everything varies from pixel to pixel. So here we have a metal ball, but for some reason, some of the tiles are missing, and those are not metals anymore. The reflections are just gone. So you can see with just the 3 textures, you can create very impressive variations from pixel to pixel and create most real-world materials in a photorealistic manner. One thing you can do to optimize your materials, especially if you use the 3D format called GLTF, that I'm sure they're going to talk about more in details tomorrow, you can pack the channels into a single texture. So ambient occlusion, roughness, and metallicness are grayscale images. So they can each fit in one of the channels of an RGB image. You can do this easily in any good photo editor like GIMP or Affinity Photo here, or Photoshop. And you can have only 1 texture instead of 3. It's going to speed up your load time. It's going to speed up the rendering as well. All right, so now I want to talk about performance a little bit. So one of the features that we have inside of our rendering engine is something called dynamic resolution. What we do is we always watch the time spent on the GPU to render every frame. And instead of dropping frames when there's too much to render, we adapt the resolution of the rendering. So we smoothly adapt the resolution both on the vertical and the horizontal axis. Sometimes we adapt first one axis, then the other, sometimes both at the same time. So what this means for you is that if you're building an AR scene, if you make it too complicated, if you have too many objects, if you have materials that are too complex, we're not going to drop frames. We're always going to favor performance over anything else. But we are going to lower the resolution of your scene. It works really well on our phones because we have really high density displays, so it's really hard to tell when this is going on. And I'm sure that most of you won't even notice as you're using the app. But basically, it boils down to, do you want to see a complex scene at lower resolution, or do you want to see a simple scene at higher resolution? The maximum resolution we currently use is 1080p. Even on devices like the Pixel 2 XL, we're not going to use the full resolution of the display because it's just way too many pixels to be able to drive physically based rendering.
Romain, I want to call out that the renderer does this automatically.
Yes, it's done automatically. You don't have to worry about it. We take care of performance in this case. Meshes, when you create your objects, it can be really tempting, especially for your artists, to add a lot of triangles to create really smooth surfaces. But we're running all of this on mobile phones, so you should be careful with the complexity of the objects. To give you a rough idea, what we call a hero object, so an object you can get really close to, should have maybe at most 10,000 triangles. But even that, if you can avoid using that many triangles, it would be great. And if you use 10,000 triangles in one object, make sure there's only one of them and not 100 of them, otherwise performance is going to suffer. And this is already with some of our early access partners, this is one of the common issues that we've seen. Really tell your artists to simplify the models as much as possible. And it's particularly important because every time we have a triangle that's smaller than a pixel, the GPU is going to do way too much work. I'm not going to go into the details here because you probably don't care, but basically we might end up doing the work 4 times, and we really don't want to do that. The complexity of the scene, thankfully in AR, you're probably not going to add a lot of objects, but if you ever create an AR scene, for instance, where you have a model of a city, you might be tempted to put a lot of objects in that city, every building or every car, every even pedestrian. What we recommend is that at most you should have maybe 100 objects visible at a time on screen. And the reason here is because we're going to run into, the CPU is going to become a bottleneck. So this is not something that dynamic resolution can help with. We avoid rendering anything that's not on the screen. We have a lot of optimizations around that. But if we have too many objects on screen, we're going to be bound by the CPU, and there's not much we can do about it, and you're going to start dropping frames. And dropping frames is particularly bad in AR. I mentioned the format called GLTF. We support OBJ and FBX. GLTF is a standard driven by Khronos. Khronos is the committee behind OpenGL and Vulkan. A lot of tools support GLTF. Websites like Sketchfab have a lot of assets in the GLTF format. And one of the reasons why I like GLTF is because in the standard, they pack the occlusion, the roughness, and the metallic inside a single RGB texture, which is something you should be doing for performance reasons. So if you can ask your artists to give you GLTF models, it's going to make, by default, your models a little more efficient to render. One thing we didn't show you how to do with our APIs, you can add lights in your scene, and you can add many, 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 many lights. This is an example of an early demo of our rendering engine running on my Pixel 2. So here I think we had something like 128 lights in the scene. So you can see that you can have many, many of them, and we can still run at 60 frames per second. What's very important is that if you add many lights in your scene, make sure they don't overlap or that they don't overlap too much. Because if we have 2 lights on the same pixel, we have to do the work twice. So if you have 100 lights on one pixel, we're basically rendering 100 frames. So use a lot of lights if you want. Make sure they don't overlap. And to do this in our APIs, you can give us a maximum sphere of influence for each light. Finally, if you use the view renderables, it's extremely convenient. You can create views the way you do it in the rest of your application. You can put them in the scene, super useful. But every view is rendered in software, and for every view, we have to allocate what's called a surface texture, and this is going to cost memory, it's going to cost CPU time, and it's going to cost GPU time. So try to reuse the views as much as possible. Don't try to put too many of them on the screen, and don't try to allocate too many of them at the same time. And finally, all the usual advice that we give you for performance inside Android application applies to AR, obviously. So don't allocate in the render loop. Don't do too much work. Be mindful of the size of your APK and all that good stuff. With that, we're out of time. There's a talk tomorrow morning, Build, Iterate, and Launch AR Apps. There's another one called Designing AR Applications that was earlier
today.
Yeah, earlier this afternoon. So come back 2 hours ago. We also have office hours. There's a code lab available online to create a similar scene to what you saw. And that's it. And if you have questions, you can find us after this talk or tomorrow. We'll be around to answer all your questions.